of identical atoms that are bonded together. Okay, so the atomic radius of an element or of atoms or a compound is half the distance between the nuclei of two identical atoms. Okay, why might it be important that we're talking about identical atoms here to get an accurate measure of atomic radii? Or the trends due to atomic radii? What do we know about the shells of elements as we move down the periodic table? The shells get bigger, right? We get more and more levels of electrons coming out from that particular atom. So if we have a fluorine molecule bonded to a cesium molecule, look at where they are on the periodic table. Fluorine is very, very top right, and cesium is very, very bottom left, or pretty close to the bottom left. So that means, does cesium have more electron sublevels or electron shells than fluorine does? Yeah, so it's going to have a bigger kind of outer shell or bigger protection against it, and fluorine is going to have really small, it's not going to be an equal atomic radii, okay? So when we're looking at atomic radii and the trends on the periodic table, we're looking at identical paired atoms. So the diatomics like fluorine, oxygen, nitrogen, hydrogen, those are things that have to be bonded in pairs, okay? So let's take a look at your periodic table now. We're going to take a look at the trends that go with that, okay? So the trends for atomic radii, they increase when you go to the right on the periodic table. Sorry, I'm going to draw it a little bit bigger here. They increase as we go to the right on the periodic table, and they increase as we go down on the periodic table. So atomic radii get bigger as we go to the increase to the right or decrease to the left, sorry.
Wait, isn't that going to the left?
Sorry, I said it backwards the first time. Okay, we're getting smaller as we go to the left. Smaller as we go to the left, but we get bigger as we go down. I said it wrong the first time, so I'm going to rewrite it up there again, okay? So it's decrease, then increase. Okay, so the atomic radii get smaller as we go to the left, and they get bigger as we go down. Can someone take a guess at why that is? We just explained it a little bit, but do we understand why it's decreasing atomic radii as we go to the left and increasing as we go down? Yeah, what do you think?
Because as you go to the left, the atoms have less atomic mass and less electrons.
More importantly, less electrons. The nuclei of it doesn't really matter, which is where the atomic mass is. The number of electron shells do, okay? And even in group 1, if we're looking at, or I'm sorry, in period 1, hydrogen and helium, and then as we go across in period 2, we have 1 valence electron, 2 valence electrons, 3, 4, 5. As we go across, we're getting greater and greater amount of electrons, which increases our atomic radii. As we go down, why do we have an increase in atomic radii also? More shells, exactly. That's what we talked about before, more shells. Okay? So what element you think on the periodic table might have the greatest atomic radii? Any idea? Which one? This one right here?
Yeah.
Yes. Okay, remember these two, what are these called right here? What series?
Lanthanides and actinides.
Lanthanides and actinides, very good. They fit in kind of right up here. Okay, actually right here. And so this, I don't even know what element that is. Number 118 would have our greatest probably atomic radii. Make sense? All right, very good. Any questions with that? Ionization energy is a topic that you'll cover a lot more as you go into college chem and as you go a little bit further with your chemistry. We'll just touch on the trend here. So what ionization energy is the amount of energy that's required to remove the outermost electron from the shell of an atom. Okay. Can someone explain to me in a little bit simpler terms what that might mean? What the ionization energy might mean? Is anyone thinking maybe about an element that might have a low ionization energy or anything like that? Which one? Hydrogen, right, because it wants to give up its electron. Very good. Very, very good. Okay, all the group 1s want to give up their electrons really easily. They're going to have a low ionization energy. Does that make sense, right? Those have one valence electron, so they want to give it away. What about fluorine? Can you predict a high ionization energy or a low ionization energy? A high, right? It has 7 valence electrons. There's no way it's giving up one, right? It wants to take one. So if we look at our periodic table this time, we can guess and we can know that our ionization energy increases as we go to the right. And increases as we go up. So increase and increase. Okay, so that's pointing right to fluorine. It has the highest ionization energy. It does not want to give up an electron. Why does it have a greater ionization energy than, say, iodine? It's which one? It's higher on the periodic table, but yes. Why? You know, Joe, what do you think?
Electrons are closer to the nucleus.
Perfect. Fluorine's electrons are closer to the nucleus because we have fewer shells. So as we get farther down the periodic table, we gain a shell every time. Iodine is in its 5th shell. It's pretty far away from the nucleus. Still a little bit of pull, still 7 valence electrons that it wants to gain one more, but it's so far away from the nucleus that has a little bit less strength to hold that electron in. So fluorine has by far the highest ionization energy. It's going to take a lot of energy for it to give up an electron. Okay. The same thing works as we go across the periodic table. As we go across the periodic table in a period, what happens to the number of protons in a nucleus? They increase. So not only do we gain electrons and makes it harder to give up, we gain protons which pull those electrons in tighter. Okay, so as we go across, we see an increase in protons, which pulls them tighter. As we go down, we see an increase of shells, which makes them easier to remove. So higher ionization up and to the right. These are probably things that you haven't heard of really before until we get to the last one. Okay, so electron affinity is an energy change that occurs when a neutral atom obtains an electron. So in a little bit shorter words, electron affinity is asking us how likely an atom is to accept an electron. Okay, that's kind of in short words what electron affinity is telling us. There's an energy change when something accepts an electron, but this energy change is basically telling us, yes, it's really, really likely to take an electron, or no, it's not so likely. Okay? So if we had to guess what our trends were for electron affinity, who would be the most likely to take an electron? Yeah, which group? What are they called? The halogens, group 7, right, or group 17. The halogens are really, really likely to take an electron. So this trend has a little bit of a glitch in it, okay? So I'm going to show you that trend. Does everyone have what they need here? Okay. Okay, in this trend on our periodic table, we see the halogens have the greatest electron affinity. They're going to take that electron very, very quickly, okay, and they want. As we go, basically for the rest of the periodic table, we see an increase in electron affinity as we go to the right, right? They're more likely to accept an electron. Hydrogen's not really that likely to accept an electron, okay? And then what about the noble gases? What do we think about those guys? Are they going to accept an electron? No, so they don't really have a value, okay? There's values for electron affinity in your book. We don't really need to take a look at those. I just want you to understand that group 7 or group 17 has the really, really highest electron affinity, okay? They're going to accept electrons the most readily. The rest of the trends for electron affinity aren't as well defined. Each kind of individual atom has its own characteristics for electron affinity, but this is a very broad general trend, that as we move to the right, they're going to be more likely to accept an electron. Uh-huh.
Okay, so what?
No, not really. As we get, especially into the transition metals, really hard to tell. Okay. Especially because the transition metals charges aren't as defined or as, I guess, regular. All right, let's move on to our last one, which we have seen before, which is electronegativity. Where did we use electronegativity in what chapter? 6, yes, but what topics were we covering? Yeah, electronegativity. We were covering covalent bonds, right? Polar or nonpolar covalent bonds. The more electronegative atom gets the electrons, right? So that makes it a polar molecule. That kind of stuff's going to be on your final. Okay, so let's brush up a little bit. All right, electronegativity. Oh, okay. Oops, missed a 9. Okay, electronegativity tells us the ability of an atom in a chemical compound to attract electrons from another atom in that compound. All right, so electronegativity plays a really important role in the polarity of certain chemical bonds. Which chemical bonds includes the sharing of electrons? Covalent bonds. So we can have a polar covalent bond or a non-polar covalent bond. Polar covalent bonds means the electrons are shared evenly or unevenly. Unevenly, right? It's a little bit kind of counterintuitive since it's polar, but they're shared unevenly, and a non-polar molecule has evenly shared electrons. What's it called when an element just gives up its electrons and hangs out really, really close to that other atom? Ionic bonds. Okay, very good, an ionic bond. They give up their electrons, but their charges now attract them close enough that we consider it a bond. Okay? So anyway, electronegativity has a certain very distinct trend on the periodic table. Does anyone know what it is? Which is the most electronegative atom that we have? And the least electronegative might be? Which one? Francium. Yeah, that's a pretty good guess. Okay. So our trend for electronegativity just goes straight up here to fluorine. Okay. As we go to the right and as we go up, we have an increase in electronegativity. So we can just draw a straight arrow right across. Okay, really, really likely to pull an electron is fluorine. And we still have our electronegativity tables. Does anyone remember what the name of that electronegativity is called? Starts with a P. Yeah, the Pauling scale. Very good. Pauling scale is the electronegativity table. Very good. Okay. Do you think the noble gases have an electronegativity value? Mm-mm. Why wouldn't they have an electronegativity value? They already have 8. They don't need an electron. They're not going to pull an electron from anybody. They don't want it. Okay, so they're not even assigned an electronegativity value on the Pauling scale.